finding. That's something that we often forget, right? Okay. So basically, we looked at this building, and to make it non-twisting as much as possible, we actually looked at uh, the possibility of, balancing the effect of these walls by using a single wall. And for that, we did this simple calculation to ensure that the centroid shear center, or the center of rigidity of the structure, lies on the center of the building. And to make that happen, we actually took the moments about the centroidal axis, and then we found the distance needed, or the length x needed for this particular wall to balance all the walls, and we found that it is equal to 3.6 meters. 3.6 meters. And we have considered that all these walls are 0.25 meters of thickness. 0.25 meters of thickness. So now today we see how we can create a model, and what are the important aspects that we have to consider when you are creating a model for a building like this. So that's what we are going to do now, and I'll stop video and then share the screen, and stop share. Okay, right. And now it's recording, is that right? Yeah. So, right. So first you have to actually start by creating the basic structure with a grid of 7.5 meters in one direction, that is this direction, 6 meters in this direction. So if you look at the plan view, what you see is here is this one, and we see whether I have defined the materials. Yes, I have defined the materials. So if you look at the materials, for each element, I'm defining a material, and actually it's the same material, but I'm defining separately, because if I want to change the quality of concrete later, I want to go for a different strength, then I can easily make that change only for that particular element. So for beams, I'm using one concrete, column, pile cap, piles, and slab, and walls. And the way that I have modeled is, I'm not going to model the slabs for load transfer. And what I'm going to do is, I will consider unit load acting on the slab, and then allocate the load transferred onto the beams using a unit load. So I'll come to that in a moment. But before that, you can first see that, I have defined different materials for all the different types. So, and then if you look at the properties of the materials, and when you say beam concrete 30, you have to be clear in your mind whether you are talking about cube strength or cylinder strength. So here I am talking about cube strength, which means the cylinder strength corresponding to that is 25. So the cylinder strength is 25, whereas the cube strength is 30. So you have to be clear in your mind whether you are defining a cube strength or a cylinder strength. So just be mindful of that. So if you want, you can just define the cylinder strength, but then the properties should be corresponding to beam concrete 25, but these properties should be corresponding to a cylinder strength of 25. So you have to be a little careful here whether you are using the cylinder strength or the cube strength. So I have defined as cube strength, but if you want, you can define it as cylinder strength as well. So if I do the design of this structure for Eurocode, then I should consider that the strength of concrete is 25 megapascal. 25 megapascal. So that is okay. And then let's see whether I have defined any section sizes. Yes, I have defined two section sizes. One is the beam of 600 millimeters of depth by 400 millimeters of width, and a column of 1000 millimeter by 1000 millimeter. So I have defined that property as well. So 1000 by 1000. Right. Okay. Then I will go to the next one. B2. Now here you can see, I have gone one step further, and that is, creating the shear walls. And to create the shear walls, I have used the function extrude. So if I delete these two shear walls, what I can do is I can click here and can say extrude lines to areas, and I have to say 0 minus 3.6. 3.6 is the floor to floor height. 1. And don't delete the source objects, because I like to have these beams to allow load transfer. So here you can see now, this way you can easily create the shear walls. And I have to make a small correction here, because in this particular model I have considered that the outer walls are 300 millimeters and the inner wall is 250 millimeter. So all these walls will be 300 millimeter. So that's a small deviation from the calculation that we have performed earlier. Because I'm going to have about 30 floors for this particular building, sometimes the use of 250 millimeter thickness may not be adequate. So I have actually gone for 300 millimeter. And also, if you look at the beam sizes, if you want in a model, you can have a few beams that are not actually there in the building. And for example, if you consider here, when you have a wall, we don't need a beam. But here I have actually added a beam. The reason is, when I want to apply loads on the loads at this particular level, then I need a beam. So for that, I have defined a small beam called additional beam. And here you can see there's a small beam that I have used, and I have allocated only a very small cross section for this particular beam. And if you want, you can even use a you can even use concrete that has no weight. So if you want, you can define an additional concrete for additional beam, and that concrete, you can say the density of concrete is 0. That means, no additional weight will be added to the model because you are using one additional member which is not actually there in the structure. And in some programs, you don't need this beam. Programs like, I think in MIDAS, I'm not very sure whether you need this beam. But in programs like ETABS, even without the beam, it can apply the load onto the wall. But in SAP, we are actually doing a general modeling. It's a general purpose program. So because of that reason, you might need you will need some additional beams when you want to apply the loads. Because if you do not have a beam and apply the load here, then it's difficult to apply the load onto the wall, because walls are in the vertical direction and you cannot directly apply loads onto this edge of the wall. So I'm using some additional beams here, and so if you look at the model, you can easily create the walls, and in addition to that, you can allocate the members for all the elements. And here you can see the beams have been added with the proper cross section, and here you can see all these beams are 600 by 400, except here, because here you can see there's a shear wall. So I have again did not allocate a big beam. I have allocated a small beam so that I can apply the loads. So any question up to this point? So then I will move to the open beam 3. So once you do this, you have to apply you have to consider how the loads are transferred onto the building, and loads are actually applied on the slabs. So slabs can behave either as one way or two way. So you have to decide how the slabs are going to behave, right? You have to decide how the slabs are going to behave. And also, so what I'm going to do is, I will consider that load of unit magnitude. Magnitude is 1, acts on the slab. I can consider that the load of unit magnitude acts on the wall, and then I can decide how much load will be transferred onto each beam. So if you want, you can make use of, there are coefficients given in BS 8110. You can use those coefficients to find the load transferred onto the beam. On the other hand, you can consider that this load will be, will have a trapezoidal load distribution. So it's a load distribution like this, trapezoidal. So a trapezoidal load will be transferred onto this beam, and another trapezoidal load will be transferred onto the same beam from the other side. So if you look at here, so this side is 6 meters, this side is 7.5 meters. So the load up to a distance of 3 meters will be transferred onto this beam. So here you can see the magnitude here due to the unit load acting on here is 3, and you can also see it's a kind of a trapezoidal load distribution. It's a kind of a trapezoidal load distribution. So you get a load distribution like this. And you can see the inner beam carries double the load of the outer beam. Inner beam carries double the load of the outer beam. And when you have trapezoidal load distribution on this beam, you'll have a triangular load distribution onto this beam, and a triangular distribution onto this beam, but the load will come from both sides. You get 3 meters here, 3 meters here, so altogether 6. And because the load will be in kilonewtons per meter, and the pressure is in kilonewtons per meter squared, once you multiply 1 by 3, you get 3 on this from this side, 3 from this side. So altogether you get a load of 6 acting in a triangular distribution. So this way, you can apply loads onto each and every beam. And sometimes, you might have a situation where in addition to the primary beams, you may have secondary beams as well. So if you are having any secondary beams, the advantage of having a secondary beam is the amount of concrete in all can be reduced when you have secondary beams. For example, when you have a span of 6 meters by 7.5 meters, what is the thickness of the slab that you would expect? Can somebody answer? When you have a span of slab of 6 meters by 7.5 meters, it's a fairly large slab. What is the thickness of the concrete that you would expect? What is the thickness of the slab? The thickness of the slab may be around will be more than 150 millimeters. And you will find that, with a thickness of around 175 millimeters, you will be fairly comfortable. But on the other hand, it's also possible to have a second beam this way, so that the maximum span will be reduced to 3.75 meters. So altogether 7.5. If you have a second beam here, then the span will be reduced to 3.75 meters. In which case, it may be possible to have even a slab thickness like 125 millimeters. So you can see, you can save about 50 millimeters of concrete. Then the question is, what is the weight of this 50 millimeters of concrete? The weight of this 50 millimeters of concrete will be about 1.2, 0.05 into 24 or 25. So I think I'm not very sure whether I have used the density of 24 or 25. I think I have used the density of 24, and actually I should have used the density of 25. I think I have used 24. We see whether I have used the density of 24 or 25. Yes, I have used the density of 24, which was the default value in the program. So for the time being, we'll consider it as 24, and later we'll change it. So if you are using a density of 25, then a thickness of 50 millimeters means a weight of about 1.25 kilonewtons per meter squared. So by having secondary beams, you can reduce a weight of about 1.25 kilonewtons per meter squared. But the importance is that, if you are going to have something like a 30-story building, this 1.25 will be repeated 30 times. Then you will find that, it can be a fairly significant value. So sometimes in tall buildings, you might consider going for secondary beams. But when you have secondary beams, the only disadvantage is that you will need certainly you will need less reinforcement because the spans are lower, but you will have the problem of casting additional secondary beams, which can actually little more labor intensive, and also fixing reinforcement also may have some little difficulties. But other than that, it's possible to use secondary beams if you like. But in this particular example, I have not used any secondary beams. And throughout the example, I think I have used a density of 24 kilonewtons per meter cubed for concrete. And I have not used 25, so we'll stick to 24. But when you are repeating your assignments, you can always use 25, which is the value specified in Eurocode practice. So unfortunately, I have used 24, and you can easily use 25 when you are doing your calculations. So then you can also see that how I have applied loads on these areas. So the loads have been applied on these areas, and also sometimes when you are using these unit loads to specify the loading arrangements, then you also have to be mindful that certain slabs may have lesser load or lesser thickness, sometimes lesser load than the other slabs. For example, when you have let's say this is an office building. So in an office building, the office areas will have an imposed load of about 2.5 kilonewtons per meter square. Whereas, when it comes to the lobby area of the lift, lobby area, and even these areas, because, in this particular building, it's most likely this particular area will be used for various services like the washrooms, staircases, all will be in this area. And so you might have to design this area for different loads, right? You might have to design this for different loads. So in that case, what you do is, you define a different unit load for this particular area. And so unit load 1 for this area, unit load 2 for this area. But these will be voids. But other than that, we are not having voids. But here again, you might have a void where the staircase is located. So here still the loads will be transferred. So that's why I have actually considered that. Some shear walls will be located in this area. So I consider that some shear walls will be located in this area, and that is the area that we can easily use for a staircase. So here I have used two different unit load values. I have used the same unit load here, but I have used, just to illustrate, I have used a different unit load there. So I can display that to you. And I can say go for unit slab 2. Here you can see I have used a different value for the load in this particular area, because this can be subjected to a higher live load than these areas. The reason is, crowds can gather here. So the lobby areas are generally designed for higher loading than normal office areas. So you can see I have used two different unit loads. So if the slab thicknesses are different, or if the loads are different, then you can use a different unit load value. And then, so basically we have the loads applied onto the structure, but only a unit load. and it follows the fact that some of the slabs are one way, some of the slabs are two way. For two-way slabs, we have considered trapezoidal load distribution, whereas one-way slabs we can use the rectangular load distribution as given here. So whatever the program you use, you have to consider that the loads are transferred this way, and some of the programs allow this to happen automatically. And some of the programs, like SAP 2000 general purpose package, it does not allow you to apply the loads automatically. So then you can apply the loads manually. So any question up to this point? Do you have any questions? Then what I do is I will go to the next step. Before not much difference, and another thing that you have to keep in mind is when you extrude here, you can see there's no support here for the wall. So when you extrude, you have to apply the supports as well, right? And also when you create the model, I'll extrude this. You'll automatically get some columns in these locations because we have created the grid and the columns and the beams. And here you can see that, I have removed these additional columns, which are not needed when you have concrete walls. So here you can see at these corners, I don't have any concrete columns. What I have is the beams. And here again, these beams are small. And there's also, you can see there's no coupling action. There's no coupling action between the walls. So in the initial model, I did not have any coupling action because here you can see what you have is a very small beam. Whereas, you can, if you want, you can provide a bigger beam than this because, floor to floor height is 3.6 meters. And the lift lobby entrance area can have a height of about 2.4 meters. 2.4 meters. The reason is the size of the lift door will be only about 2.1 meters of height because you don't need anything more than 2.5 meters, 2.1 meters for the height of the lift door. 2.1 meters means 7 foot. So you don't get that tall people. So that is enough, 2.1 meters. And generally to do the fixing of the lift, we keep a wide of about 2.2 or 2.25 meters of height so that all the additional panels of the lift can be fixed. So when you are entering the lift lobby, you can have a opening height of about 2.4 meters. So which means, we can have a coupling beam of 1.2 meter depth at these two locations. Here you can have a deep beam. Here you can have a deep beam. But for the model, I have not used that particular aspect because I want to introduce it later to show you the effect of coupling action on the building. So we'll change this later, but time being, we'll keep it as it is. Janit, can
Yes,
you
sir.
hear me? Yeah. Is there
Yes,
a
sir.
problem with this
Yes, I can hear you.
40-minute limit or something now with Zoom? Or have they fixed it?
Uh,
So
I'm not sure,
we'll
sir, but
continue.
there was a message. Yes, sir.
If there's a problem, if the program stops at 40 millimeters, what we do is we'll meet after lunch, right? If the program crashes, right? Or stops at 40 minutes, right? And then otherwise we'll
Okay.
continue because now 40 minutes might come around 11:55. So if there's a 40-minute limit, we'll set up additional links for the afternoon lecture, right? Right. So if it crashes, we'll let it go and we'll meet after lunch, right? Okay. Otherwise, we'll continue. Okay. We'll see because whether it crashes or not. And if it crashes after 40 minutes, I'll set up a number of links for additional links for the afternoon lecture so that we can go on 40-minute slots, right? So let's assume that they have fixed it, they have sorted it out, right?
It didn't happen yet, so I think it's okay.
It's okay, maybe okay, right? We'll wait and see, right? Okay. So now you can see, have a look at the model, and then there are a few other important things that we have to consider. And here you can see I have modeled only the beams and columns, and I have not modeled the slab. So if I do not model the slab, then it's not possible to indicate to the program that there's a slab here. So what I can do is I can deal with this in two ways. One is, I can define a rigid diaphragm at this particular level, rigid diaphragm. So the moment I define a rigid diaphragm, the program considers that this there is a slab. On the other hand, I can actually model the slab. But the problem with modeling a slab is in a general purpose program like SAP 2000, when you model the slab, slab will be modeled only as a plate element or a shell element, and it will be connected only at these four corners. So you cannot actually get the proper load transfer. So because of that reason, to transfer the dead weight or the self weight of the slabs, we do not model the slab. Because if you want to have a proper load transfer, then what you have to do is you have to divide all these beams into small pieces like say 0.25 meter length or 0.3 meter length, small pieces, and have a grid for the shell elements so that you will divide this large slab into so many small squares or rectangles, and then you apply the load directly onto the slab. The problem is, when you try to do that in a large building having 30-40 floors, each slab will have so many shell elements. And when you consider one particular level, there will be a lot of shell elements. And when you consider about 30 to 40 floors, there will be enormous number of elements. And because of that, the program can become fairly slow when it comes to running. So because of that reason, generally we do not try to divide the slab into small segments, and rather than doing that, we can use different tricks. And in some programs like ETAPS, the program can do the meshing or breaking the slabs into small segments when the program is run. So that is also possible in some programs. But in SAP, when you are using when you are doing the modeling, one of the options available for you is to just do the modeling with a concrete slab, large concrete slab, but make it weightless. Make it weightless. But we'll allocate only the mass. So then you'll ask, why do we want to allocate the mass? So at each floor level, we are getting a 175 millimeter thick slab, and that slab can contribute to the mass of the structure. So when you are doing an analysis, we are looking at two different properties. One is the static response, the other one is the dynamic response. So when you want to know the dynamic response of the structure, then we have to determine the natural period of vibration of the structure and also a natural period of vibrations in higher modes of deformations. So you can have a number of mode shapes, and generally you will find first 3 to 4 mode shapes will be dominant, whereas the other mode shapes will not dominate. So to determine the dynamic properties, you need to have the correct mass of the structure. Correct mass of the structure. So how do we find the mass of the structure is, you have to ensure that all the elements that are there in the structure are actually represented in the model. And if you are not going to represent any structure, any component properly, then you have to add it as a mass. So I'll show you later how to add more mass onto the structure. And if you want, you can actually select a point and allocate a mass. On the other hand, you can actually allocate it, ask the program to derive the additional masses from the loading that you have specified. And we'll make use of that particular method. But I'll show you that, why we need to adjust the mass. And one of the important properties of information that you need to find the natural period of vibration is the mass of the structure, not the weight of the structure. It's the mass of the structure. So we can easily get the mass correct if we represent all the elements with the correct dimensions. So what we do is, we'll represent the slab as 175 millimeter, but we'll make it weightless, but we'll keep the mass. So if you look at the material properties for slab concrete, here you can see the weight is considered very low. I'll show you another concrete, beam concrete. Here you can see weight is considered as 24 kilonewtons per meter cube, and mass goes as 2.4 tons per meter cube. Whereas in the next one, in the slabs, I have converted to a weightless slab, but the mass remains. So when you define the slab, there will not be a load transfer, but the mass will be represented accurately. So I'm going to use that particular method. So what you have to keep in mind is, always when you are using a program, we cannot say you will specify SAPCO or ETAPS or MIDAS. So always just think in terms of fundamentals and see whether you have got the mass of the structure properly allocated. And then you also have to see whether the weight of the structure has been allocated properly. So you have to check those. And then I'll go to the next one. Looks like the same. Right. Now you can see I have allocated all the slabs as well. All the slabs have been allocated, but slabs have no weight but the mass is properly allocated. So the program can determine various periods of vibration in different directions and also at higher modes. So now I added the slab, and then we also have to see the different load patterns that have been defined. And so we, to define all the slab loads and all that, we have the what we call the unit slab. Then there are two different slab types, and maybe the same thickness, but one slab number 2 is at the lobby and it's subjected to a higher. Slab number 2 is here and it is subjected to a higher vertical load. So because of that reason, I have considered different unit slab load for this particular area. And in addition to that, you can see now I have considered the wind load in X direction and wind load in Y direction. And so there's a small mistake here. So this has to be defined as a wind load and modify. And this also has to be defined as a wind load, modify. So these have to be defined as wind load. So I have defined those as dead loads, which is wrong. So say okay, and I'll save this also, save. So now you can see we have the model of the building for one floor, only for one floor. And then we have to see how we are going to create the load combinations, So for that, we'll see what are the different load combinations that we have to consider for the building. So if you look at this particular building, so we have the self-weight, GK values, and we have the imposed load or the live loads, those are GK values, and we also have wind loads, so that's those are WK values. So in Euro codes, you can have GK always as a permanent load. GK is permanent, and it can carry a factor of safety of 1.35, and QK will be variable, and WK also variable, and for variable loads, the factor of safety is 1.5. So you'll have a load factor of 1.5, factor of safety of 1.5 for those. But only one of them will be dominant. When this is dominant, this will be the additional variable load, and then you have phi naught value and phi 1 value, and this will be phi 1 value will be 0.5, and here the phi 1 value will be 0.7. So we can have different load combinations. One is, building has been completed, nobody is there, so we have only the GK, and maximum wind will act this way. So wind WK will act this way. So you can have a load combination. First one, 1.0 GK plus 1.35, 1.5 WK. So that is the case. That is case one. And what happens in case one is this side can go into tension. So if this actually checks whether tension can occur on the windward side, because the building is going to be deform towards the leeward side. So building is going to move like this, and then there's a possibility of tension occurring here. So this will tell you whether tension can occur in the building. And then we can have a case where GK is there and WK is there, and so WK is 1.5 times WK maximum value. GK also will be 1.35 times DK. So I'll not define it as a case because when you look at the next case, you are going to get 1.35 GK. Here you get wind, so it is 1.5 times wind. But you will also have QK, which is 1.5 multiplied by 0.7 times QK. 1.5 multiplied by 0.7 times QK, which will give you a value of 1.05 times QK. So there's a possibility of all these acting. And when you compare these two, now you can clearly see this particular case will be more critical because 1.35 and 1.5 are already there. But here you get none the additional loads. So I'll consider that this is case 2. So I can have a load case 2. And then, we can go to the other direction. That is 1.35 GK, and the vertical loads also will have 1.5 times QK. And in addition to that, we will consider wind is also acting. Then you get 1.5 times 0.5 times WK. So it will be 0.7 times. So this is another case. And here you can see these two cases are clearly different. So we'll call this case 3. And then we can also have a case where only dead load GK and 1.5 times QK is acting. So we consider this as case 4. So here we are not considering a wind load, we consider that only the vertical loads will act. So we can have 4 different load cases. And after lunch, I'll show you how to create all these different load combinations that we need. So this will form the basis. So this is case 1, this case 2, this case 3, and this case 4. So case 4. And this is 1.35 times 35 times GK, and here you get 1.5 times QK. So with that, shall I end the first part of the lecture, and can you use the second link to join after lunch?
Okay, sir.